Alright, so we have learned so far that the relative energy of the orbitals makes it fill up first. So we know that the energy of the orbital 2s is lower than the energy of the 2p. This is why it fills up first. The next question is, what kind of physical consequences will that have on the atoms? What kind of characteristics the atoms and the elements will have depending on if the orbitals are on the 2s, the 2p, or the 3d, you name it. So let's look at first at the atomic size. How does the atomic size change depending on where the electrons are? So if we click here, you can see that the size of lithium, beryllium, boron. So as you go from the left to the right of the periodic table, the size of the element will decrease until it reaches another row. So here from sodium, magnesium, aluminum, silicon, and then we may be able to explain why aluminum and silicon the difference is so little, but then it keeps going down: phosphorus, sulfur, chlorine, and argon. And also we may want to explain why chlorine and argon, why is it that argon kind of doesn't follow the trend? It's a little bit larger than chlorine, but we can keep adding more and more rows, and on the fourth row of the periodic table you may see that in the transition metals it's fairly similar. Okay, these are all trends that we should be able to explain in terms of the atomic size. What we have seen therefore is that if this is the periodic table, what we have seen in that graph is that as you go from left to right, generally the size decreases. And if you notice, as you go, so let's just look at it again. If you go from period down the period, so lithium, sodium, potassium, that is lithium, sodium, potassium, the size increases. The size increases. So in this course, it will not be enough to remember this trend. In this course, what is important is to understand is why that happens. For example, if this is hydrogen and then lithium and then sodium and then potassium, why is it that as you go down the periodic table the sizes increases? Well, notice that in potassium and in sodium and in lithium, so the valence electrons in this one is in the 2s, the valence electrons is in the 3s, in potassium the valence electrons is in the 4s. This means that this number, the principal quantum number, changes, and it's larger. Remember, the principal quantum number talks about the size of the orbital. So this orbital is larger, therefore the size of the whole atom will be larger because the electrons are farther away. They are in a larger orbital. It may be a little bit more intricate to understand why is it that when going from left to right the size decreases. Well, in this case, as you go from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, why is it that the size decreases? Well, notice that the electrons are in the 2s and the 2p, so the size of the orbitals is similar. But notice as you go from left to right, the size, the charge of the nucleus, increases. So this means that if you keep adding positive charge in the nucleus and the electrons are at the same size, the nucleus will be able to attract those electrons more strongly. Therefore, it will shrink the element. So as you go from left to the right, the nucleus attracts the electrons more strongly. This means that the electrons will feel more attracted, they will get closer to the nucleus, and this is why as you go from left to right the size decreases. You may see some exceptions, and it's because as you keep adding electrons here, they will start bothering each other. So what you saw, let me remind you, why argon in here is larger than chlorine or neon larger than fluorine is because at some point there is a lot of shielding among electrons, a lot of repulsion, so the electrons will repel each other and kind of get farther away from the nucleus, therefore increasing the size. Let's practice a little bit. Well, just to mention some application, you may have heard about potassium channels and sodium channels. Notice that sodium and potassium are very similar. The only way that the potassium channels and sodium channels can distinguish among sodium and potassium is because of the size. In here there's some specific binding elements that will just coordinate potassium or sodium exclusively or most exclusively because of the size. So now let's run some examples. In this case, we just have to rank the elements in terms of their size. In this case, it says decreasing size. So let's do the first one, which is the easiest: calcium, magnesium, and strontium. So this is magnesium, calcium, and strontium. As we say, as you go down, the size increases. The size increases. Therefore, the size of the strontium will be larger than the size of calcium, will be larger than the size of magnesium. Let's do another one that may be a little bit more intricate, like this last example: strontium, calcium, and rubidium. Strontium, calcium, and rubidium. In this case, we know that strontium is going to be smaller than, strontium is going to be larger than calcium. I apologize. Rubidium will be smaller than strontium. I'm not having a good day today, apparently. That's not correct. Strontium will be smaller than rubidium because it's more to the right of the periodic table. Yes, so strontium, because it's more to the right of the periodic table, it's smaller. And if strontium is larger than calcium, as we said, because it's lower, it will be, so calcium will be the smallest, followed by strontium, followed by rubidium. I apologize for the mistakes at the beginning, but hopefully this makes some sense. I will insist on to understand why is it that we have these trends. Okay, so let's make sure that we do not only remember we do not only remember the trends, but we can explain why, because there will be some exceptions and we have to be ready to explain why.